Okay, so can you see the window?
Yes.
So basically we start with a new build tray. Let's
Wait,
specify the
I don't see
folder.
your screen.
Oh, sorry, I forgot. Wait a minute. Screen 2. Can you see it now?
Yes.
Okay, so let's go to desktop, temp. Okay, so we go with a default build tray. Click on OK. Now in the
Okay.
assignment, if you can see here in the additional information, you can see that the build envelope or most common envelope is 250 by 250 by 250. So we'll just initially set that. Take STL build tray. Now go here, right click on it, click on properties. You'll see the height here, change it to 250, the length to 250, and the width as well to 250. Set these two to minus 125, like the half of 250, and minus 125. If you click on
Yeah,
apply,
but
you'll
what was
see
that all about?
what?
What was that all about?
I'll show you. I'll show you. So we have a most common build tray according to this file that should be 250 by 250 by 250. The reason for doing this is because we will be nesting, and by that we'll know how much parts we can place in one build plate. So the build time will be lowered comparatively for one part, right?
Hmm. Hmm.
Okay, so we have set up this envelope. Now we'll add the part. So we go to the folder, search for, oh, we need to do import STL file. Go here, temp, this is our file, click on OK. So basically you just keep it there. Then you go to file and modeling. In modeling, then you go to design for additive manufacturing and then click on part orientation. So here you select the method. So for now we are using the powder bed fusion method. Click on next. Select what all checks you need to have. Mostly keep all selected. Click on next. Maximum overhang angle is 45. That's okay with us. This is keep it like if you're using Inconel, read those properties and put those properties here. I'll just go ahead with the default ones. Click on next. Maximum overhang angle. So if it will show you like um, if your part is overheating, the this will be the maximum overhang angle. If it exceeds that, it will start drooping down. So this angle specifies that. Then select the body. This is our body. Here you will have for this orientation how much surface area is taking it is taking on the build plate. Then the support volume, like if you put supports on here, how much volume of material or how much space will require in centimeter cubes. Then the print time, you'll see it here, hours and minutes. Then the overheat area, like which sections are getting overheated, that is the area, and it will show you here. Then you go to next, and you basically set this to high accuracy. But for now, just to make it quick, I'll just set it to low because this takes time. And then you just like that. Uh, but always set it to high. It will take time, but it will give you accurate results. Then you start calculation, and then it will take some time, and it will give you the orientations on the basis of this coordinate system. So this is your default coordinate system for now, and the best ones will be shown. Like I'll show you when it's done. Let's wait for the results. If you go low here,
NetWeb does NetWeb does it so much faster.
yes, and so much better. But this is more important because it considers that the part is connected to the build plate, which is more important than the volume it's consuming. So if you use NetFab, it only considers the volume, but not the area on the build plate. So your parts may be hovering over here somewhere, only connected by supports to the build plate, and that creates difference in parts.
Hmm.
But in this case, if all your parts are connected to the build plate, it will have same properties throughout the section or throughout the height. But imagine that if you have this part and it's getting stacked vertically in this direction, same part stacked in vertical direction, the one close to the build plate will be stiffer actually than the top one because the grain size increases as you go up, and that reduces the stiffness. So you will have different properties even if the part is same. Did you get it?
Yeah, I got it.
Okay, so we have the part. So this is our
Hmm.
uh, original coordinate system, and this is the coordinate system that NX has given us that is best according to it. Then we go to final orientation, and you have all these options. So if you have to optimize the surface area, you just click here and it will give you the coordinate system for that. And you can also see that surface area we are using the minimum one, but the rest is higher because we are optimized for surface area right now. If you go to print time, it will choose the minimum print time and give you that orientation. Similarly, if you go to support volume, it will reduce the support volume. Like this will be minimum and the rest will be optimized accordingly. And if you go to overheat angle, it will reduce the overheat temperature or the area. And this is the orientation it will take. But the best ones are these ones. So they consider all of the properties, like you can provide the weightage, like what's important to you. You can just slide it, like you don't want surface area to be that important, so you can slide it down, and then if you click on one, it will give you the orientation on how you should orient the part in the on the basis of a coordinate system. So let's just keep everything at 100. So we are considering everything, and this is the best orientation that we have. So this orientation, you can print it, create a print CSYS. So now it is printed on your build plate. Click finish, and you can see it here. Can you see it? So basically our
Yeah.
Z is this, but ideal is this side. So we'll just click on the part. Then we go to application, additive manufacturing, move part. Select the part, go to your front view. Now just rotate it. There. So we have X, X, Z, and Y. So it is oriented perfectly. Click on apply, but it's not on the build plate. So we go again to the front view, click on the part and move it upwards. Click on apply. Okay, there we have it. Just save this part. Okay, we have saved the part now. So we just have one of the solutions, right? But what we need to do is we need to select three orientations, so we can just basically do the 1, 2, and 3. We can create those CSYs by from the same process. So select 1, 2, and 3, take a screenshot of the orientation, and then you can use those orientations and do the same process that we are going ahead with. Now let's get back. Now what we need is the nesting density. So for nesting, you have one part, then you click on move. Instead of move original, we'll switch that to copy and create around 30 of these. All right, and click on OK. And yes, so it will create 30 copies and place it over the same space as it is. So you'll not see 30 of these parts, but they are there. Once
Hmm.
we get those, you'll see it here. Okay, we have it.
Oh.
So we have 30 parts. Now we need to nest it. And you can do that by using pattern part or automatic nesting. So I've used automatic nesting and the results are the best for nesting. So you can use 2D or 3D, but for our case, it is given in the file that it should be connected to the build plate and not stacked in Z direction. All right, so there shouldn't be any part stacked on one another in Z direction. Okay, so no part on one another. So we just stick with 2D. We can set Z level to 2 mm. Z level is basically the height from the build plate. The distance between the parts is 5, but you can go with 4 or 3. Then you have the wall distance, or the like, imagine a imaginary plane parallel to these walls and it is offset to 2 mm inside, so it will fill that volume. Okay, so we have the build volume 250 by 250. Then we have the limits or constraints, and then we set it to like 5 minutes. All right, and then we select the parts. Okay, just click here and it will select the parts automatically, and click on OK. Now we just wait and watch. It will show us the uh, process over here, like the percentage of completion. You will see parts moving here as well in a moment. Let's just wait for it. I should have set it to 2, but okay. It will give better results if you give it more time. So it can fit more parts if you give it more time. So I'll suggest you to go with 10 or 15 minutes. So by then it will either tell you that this is the best I can do, or it will go till 15 minutes and give you the best, like it will fit the most parts in the same volume.
15 minutes, like you can set the time, like after 15 minutes, it automatically stops, right?
Yes,
Okay.
now it will stop in 5 minutes, which is long actually. Oh, we forgot to change one setting, but okay, we can do it later on. You can see what happens when we change the options.
So every 30 parts will be in the same orientation as the first one, right?
Yes, for this case, because we forgot to change one option, uh, can you see it here? The constraints fixed rotation. So if we had
Okay.
changed this to like plane or something, then it would have like rotated the parts as well.
Okay.
We'll change it in the next iteration. Let
So
it
if we
complete
are
now.
rotating it, the
Mhm.
stiffness of each part will be different, right?
No, it won't.
No?
No,
We
because
are
anyway,
rotating in Z direction.
oh, if you rotate it in Z direction, then yeah, then the properties will be different. So I'll suggest you to use 2D, and
Okay.
there is a plane option here. But if you go with 3D, it will rotate in Z direction. So don't go with 3D. And with 3D, it can also stack parts in vertical, which we don't want. So that is why I'm using 2D here. Let's wait for it. Till then, I'll show you the netfab thing. Oh no, oh no, 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 no. Hold on, it's opening. Till it nests the parts, we can get a demo on netfab actually. So select the printer. Let's take Aconity MIDI. And then we add our part, same part. Let's go to top view, place it in the center approximately, and then go to orient part. Put your values here. We need Z height to be 2 mm, critical angle to 45, smallest rotation 90 degrees. Go with basic ranking, it's good enough. And then search for orientations. It will calculate all the orientations and give you the best ones. Let's wait for it.
The type of printers is already there in NetFab, or you are
Yes,
selecting it from somewhere else. I
no, it's
just
already there.
installed the NetFab.
It's already
So,
there. So, or else you can add the printer as well. I'll show you
okay.
where you can add the printer. Okay, let it complete. Oh boy. Okay, so according to NetFab, this is the best orientation, which
It's a
is what?
the inverted position of NX, right?
Yes, but
Mm.
according to me, this is the best one we can go with. See, these are the orientations that we have that are good according to NetFab. So you can
Oh,
use these
11
as well.
oriented. Okay.
Okay, and to add the printer, you can go here and search for your machine or add a machine. Search from here. There are a lot
Okay.
of machines and you can add those. Okay.
So automatically the build volume, build plate, everything comes along with it.
Yes, everything comes.
Okay.
I don't know
Mm.
why didn't we get this software, but we haven't. So there's that. Close it. Just close it. So as you can see here, that NetFab has nested 21 parts, and the not nested parts are basically kept outside.
Oh,
As you can
okay.
see here, it will kick out the parts. But now we'll again do the same thing, automatic nesting. It has selected the parts, but now we'll change it to fixed bottom plane. All right, now it will flip the or turn the parts in 90 degrees as well. Let's just set this to 2 minutes and click on
Okay.
OK.
Oh, what does the fixed bottom plane constraint means?
It means that it will rotate the part but not in Z direction. It will rotate the part in the XY plane.
Okay, fine.
You'll see what happens.
Mm.
Hmm.
You are having lab tomorrow, right?
Yes, we have a lab tomorrow.
What do we have? We're taking out the sintered parts.
Yes, and
Yeah,
then
and
squashing them.
doing the compression test.
Yes.
You, Udit, and all are done, right?
Yeah,
So
What
now
about your
only
report?
report and this assignment.
yes, report and assignment. Mhm. We need to get the question paper of metals and ceramics.
Oh yeah. Ask Christina
Yeah.
Can you
because
see the parts moving?
if
The parts
the
are
thing
moving,
is,
right?
if we ask Christina,
Mhm.
the guy doesn't know that we have got the paper, and he'll set the paper similarly.
Hmm.
That's what happened with Jonas Lind.
Yes.
If you find it, just put it in the group. We'll do it.
Yes. Mhm.
Earlier it fitted only 21 parts. Now let's see how many parts it can fit when you select fixed bottom plane. We can see it here as well. It has already
So,
nested 23 parts.
hmm. When you're done with 15 minutes, how maximum how many parts you are able to fix in the build volume?
23.
26,
3.
23. Hmm.
Yes. I guess that's the maximum it can do. It can't go any further.
Hmm.
Maybe if
And
you
we can't.
select maybe if you select 3D, then it
Hmm.
can do it, but it can stack parts vertically, which we don't want.
uh, they were instructing in the assignment, right? We
Yes.
don't want one on top of another.
Yes. Okay. Okay, it's done. So it says that 23 parts were nested, 8 parts were not nested, but we have 30 parts, right? Oh, so one including. So it just creates 30 more copies. All right. So we have the nested parts here. That's a pretty good nest. So we go to
Hmm.
the front view,
What is that line in the side? Delete that.
select these, delete it. So these are our
Hmm.
parts. All right. Then we again go to modeling, design for additive manufacturing, do the same orientation stuff. Next, 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 next.
So we are doing the orientation stuff for every part right now.
Yes.
Oh, so okay.
No, not for every part. I'll tell you what we are doing. You just select it all these parts one by one.
Did we mention how much will be the distance from the wall of the build volume? Did
Yes,
we?
yes, we did. It
Okay,
is
I
2 mm.
didn't. Okay, okay,
I'm recording the video, you'll see it later.
okay.
Okay, so basically you select all the parts and then take a screenshot of this because it is important. Here you will find the build volume, you will find the print time, and you will find the surface area as well. So we need these numbers to calculate the costing.
Costing. Okay,
Yes. So to see the costing, you need to calculate the build time. So you have job
okay.
volume, which you can get from here, support volume
Yes.
and the part volume. So just add those,
Hmm.
and then where did it go? Then you have these two printers where we have the printing speed. So you have the volume, you have the speed. So you just
Okay.
divide the volume by this number and you will get the time. All right.
Okay.
That's what we need to do. Then you can calculate the job cost and the material cost as well using all the details here. But for that, we need information from here. All right. Okay. So that was for the orientation part. Then what's the second question? Where is it? We have the nesting density. We can calculate the cost per part. Okay, we have the support strategy as well, but I'll show you how to do it more accurately. We can talk about part qualities, like if it's stacked in this position, we will have lines like this, the layer lines like this. And if it was horizontal, we would have along the length. So along the length will be better in some cases, or like depending upon the load and the characteristics we want. So you can say that we need to know the characteristics that are required, like will the part be in compression, will the part be in compression. So depending on that, the orientation can matter. All right. So but for now we don't know what this part will be used for. So we are just going with like minimization of printing time and that sort of things. We're not talking about part quality now. Part
Okay.
quality depends on what application it will be facing. If we have that, we can make changes here. All right.
Uh, okay. Kautuk, here in this orientation, we have the lowest surface area per layer, right? For each part.
Yes.
Does that gives any advantage for the quality of the part?
No. I
Hmm.
mean, not directly. Maybe due to some post-processing operations, or
The thermal stress will be low, right? On the.
I think it will be higher because only one part is touching the build plate, and it's like an inverted triangle here,
Hmm.
and we don't
So
need that.
temperature gradient will be higher, you are suggesting.
Yes, the temperature gradient will be higher, as well as it will face like the layer will be heated for a longer period of time as compared if it was placed upside down, because then you'll have two areas at least transferring the heat to the
Hmm.
build plate. But for now, we are
Hmm.
having just one area and the support structures, but the supports aren't that good for transferring the heat.
Hmm. Okay.
So what we'll do is we'll select the upside down version and then move ahead with the other tasks. Uh, Now we'll talk about the support strategy. So I'll close this. Part and components, no clues. But you can continue with that as well. Just delete all those parts and then continue. But for now, I'll go with the new file. Yeah. Build tray, apply. Okay. Then you add the part. Sorry. You can add the STL file. Click on OK. You have the file. Go to front view. Move part. Click on the part. Rotate it. Did it crash? Whoa. What is that? Oh no.
Copy
Oh
original, move
no.
original.
Okay. Thank you. Thank you for that. So always check this one. Set it to 90 degrees. You can apply it, then click again and move it. Keep it a bit higher. Did someone join?
Moyo.
Okay. Hey Moyo.
Yeah, what up?
So we are recording this, so you will have the part that you missed at the start later on.
Oh,
All
okay.
right.
All right. Thank you.
Okay, so we have oriented the part. Now we need to do supports. So we go create supports, set it to automatic, select the part, and click on apply. Okay, so we have the supports. Now we need to edit it. So basically we select these two, or let's do it one by one, and change it to volume, because these supports are not dense from inside. So when you change them to simulated supports, the heat transfer from this will be higher as compared to this one. So when you have a higher heat transfer, your part will not overheat as much as it would have heated if you used these kinds of supports. So in my opinion, the bottom faces or the lowermost parts that are touching the build plate, those should be volume supports. That is what I do for each of my
What
parts.
what type of supports do they provided now? What is this called? Hybrid. What
No,
is this?
this is block support. You can
Okay.
see it here. This is block support.
Okay.
Can you see
Block support.
that
Okay.
this is a
Block
block
support.
support? Okay, and this is volume support. So volume supports are better at heat transfer.
Hmm,
But
yeah.
the machine,
Reduces.
but to remove them will be so much pain.
Yes, it will be, but your part will be like less stressed. Like the manufacturing stress will be lower if we use volume supports at the bottommost piece. All right.
Mm.
So we do that. For now, let's hide the build plate or the build volume. This gives us more flexibility for editing the other supports. So now we have these supports, and some of the supports are not good for simulation, like this one. So if I click on this, go to process simulation, generate simulated supports, I've selected that one, and if I click apply, because of this kind of structure, it will say that the part is not, like, it will give basically some error. Yeah. So the support generated with mismatching part and faulting body. So it says that the body has some kind of fault. So we close that and clear simulation support. We go one by one, we edit it, go to support angle. If it's not visible, it's basically because you need to click this, go to support angle, and we select, oh, wait, edit, go to specify orientation, move it, and then click on that arrow and specify small values like 0.5, then go 0.1, then go 1.5 till it looks like it's completely landed on a flat surface or approximately a flat surface. So we move this by 1.5, click on apply.
What did you do again?
Yeah, I'll show it to you again, and it will be
Okay.
in the video. So if you see, we had this kind of structure earlier. Now we don't have that. So this is a better support than what we have here. All right, we just tilted the support from down here. Like it's like we are fixed over here and we are just dragging the supports to inside or in this direction. We are just pulling it to this side. All right.
Okay, okay. Hmm.
Then we go edit, specify, zoom out, click on this, and we'll go minus 1.5. Okay, it's
Oh,
still
we are going
slightly outside.
inwards.
Go -2. Okay, that's good enough. Click on apply. There. Now similarly, if you see this support, it's it might give us problems or it may not. Let's try. Let's generate support, select this one, click on apply.
Mhm.
If it gives us errors, yes it does. So we move that as well. Clear simulation supports. And we did not try it for this, right? Let's try it for this. We changed it, but we'll see if it has any benefits at all. So now we click apply, and there we have our simulated support without any error. All right.
So, what was the error initially? What the software was telling us about the error?
When the support is like on a very slanting surface, it gives you error. Like it cannot compute that
Okay.
kind of simulated supports.
Hmm.
If the
Okay.
base is approximately flat or like this, it can simulate those. But if it's like very slanting, like these supports, if you see here,
Hmm.
it's landing on a very slanted area. So the software cannot generate the simulated supports. So we need to help it to like find something.
So we need to provide a flat surface for the bottom part of the support, not a
Yes.
slanted part.
Yes.
Okay, fine.
So we
Hmm.
click apply to here as well. Let it compute. It will take some time. Okay. See here we have moved it, but it's still doing this structure. So we need to move it further. All right. So let's just do undo. Select it, edit it, click on this, move it to minus 0.5 again. Click on apply. Close. Now let's try again. Simulated supports apply. Still giving us errors.
I think it was in the opposite direction. It increased.
No, no, we are getting there. It will just take some time. So you need to
Okay.
play with this. Go to 0.5 further. You can apply. Then generate support, select it, click apply. Maybe instead of cancel, I should click on OK. Control Z, edit 0.5, apply, and OK. Is it moving? Let me try some manual things. Okay, it is moving. Okay, whatever you do, some supports won't accept the changes. So just let them be alone. Then you go to generate simulation support, select the bottom ones. 2, 3, 4, 5, 6, 7, 8. Not this one. I'll show you why. Click on apply. You basically need to play with the software to know how to work with it. Okay, so we'll save it because we have done a lot of effort on this. Now select that one. Let's see what happens. Okay, it gave us no errors, so that's good as well. Then I'll show you where it goes completely wrong. Let's select this one, generate, click on apply. It will create a vertical bar like through the body. Can you see it?
Yep. Yeah.
Oh.
Yeah. So there we have some problems and we don't want that. So some supports will be transferred like it, some supports can be simulated, some supports cannot be simulated like these ones. So we just leave them alone.
Okay.
That's all we can do. Then go to process simulation. Select the body. Click on OK. All right. We have our part. Go to powder bed fusion. Click on global settings. Simulate without powder, and you know basically you know this process. Yeah. Or should I do it? Let's do it. Let's do it. Let's say 5 slices for now. Set it to 0 because if you set it to 3, it won't simulate the bottom layers. And set a, like leave this one alone. Click on OK. Now remember that we created 5 slices in thermal, in the thermal slicing. Go to mechanical, and it is suggested by NX that you should use same number of slices for thermal and mechanical. So here we sync Z with thermal, and in the slice we will just calculate. We know that our height is 129.6989 and we divide it by 5. So this number we'll just put it here. What was it again? 25.9397. There we have 5 slices. Click on
So,
OK.
Kaustubh, for
Yes.
initial assignments, I was not considering my bottom supports inside the thermal slicing.
Yeah, that's okay. That's okay. I mean, that does not make that much of a big difference, but it still does.
Okay.
Yeah.
Mm.
Go to meshing. I'll select a coarser mesh for now. You can use same mesh for thermal. I'll suggest you to use it. Let's go with 2 for now. Let's do just 3. I'm going with a coarser mesh just for the simulation, like the video purposes, else the video will be too long. And I'll explain to you what these sections mean as well. So if you are considering a smaller section like this one, let's just consider this tube. The radius on it is too small. So what it does is, if you have an element size of 3 mm and if you set it to 50, it will create like 50 sub, like it will discretize the one element 50 times just to like encapsulate this area, and sometimes we don't need that because this mesh size goes too small. Then you can switch that to, let's say, like 30, and then you will have a coarser mesh over here that increases your simulation time. Then in the minimum element size, it will set like how small the smallest element can be, and for now it can be 5% of this. Okay, so that is pretty small. I'll go with 20 or 25, so I get evenly distributed mesh overall, and plus it reduces simulation time. And you can small feature tolerance, I just leave it alone. I don't know how to use that yet, but this might be like, don't do anything with it. Then click on supports and set the same value or lower value here. So we are using 3 there. I use 50% of that for the simulation supports and click on OK. It will start simulating. Don't forget to click OK here and then leave your PC if you want to. Else you will be wasting a lot of time and return back to frustration because it won't mesh the part until you click OK. Okay, it is doing something. Let's wait for it. I should have gone with 5 mm mesh. It is going to take a lot of time. Yeah, maybe I'll just cut it out from the video. So Moyo, how's the assignment going with you? Moyo?
Hello, can you hear me?
Yeah. How's
Yeah,
the assignment going?
I haven't started my assignment two yet.
Okay.
Yeah,
You're
but
still with one?
for one, I've done one. I've done the
Okay.
simulations for assignment one.
All right.
Although,
And yeah.
yeah, on generating support in
Mm-hmm.
my assignment one,
Mm-hmm.
I realized that when I changed the block to volume for the base support,
Yes.
I couldn't mesh. I couldn't mesh the component. It was
Why?
more like giving me errors when I tried meshing it. But when I left it at block, all the support at block, it's meshed. I don't know why.
Did you simulate the supports when you created blocks?
Yeah, yeah. When I created blocks,
Mm-hmm.
I simulated the support.
Well, that's weird. But NX is weird.
So I didn't just choose volume anymore.
Okay,
I made everything block and then it meshed completely. I don't know.
all right. Let's see what tasks we are doing right now. So we did the support strategy thing right now. Then the part quality is basically it, like we don't need software for this. It's completely logical. Then select the orientation you consider best overall. So from here we know the orientations which are best. Then you select three of the best, like 1, 2, and 3 from the orientation that I showed you. You select these three and do the second part and select the best one from here. Like if you're considering costing as your preference, then the lowest cost per part orientation you can use it and do the simulation here. Okay, we are doing this right now. For this orientation, study the effect of mesh and voxel size. So basically what you have to do is change different mesh sizes, like go with 3 mm, 2 mm, 1 mm, and change the number of slices from 5 to 10 to 15, but don't go beyond 24 or 30 because it takes a lot of time. It takes up to like 2 hours just to mesh the part, and sometimes it won't even mesh the part completely. It will just fail in between. So it's no use doing that. It's still meshing. I've selected 3 mm and it's still going on. So you just imagine if you go lower, your system will die basically. See, mesh meeting failed to create glue coincident conditions. Exiting support meshing process. Okay, so it
That's
could not
the
mesh the
that's the
supports.
error what I got.
Yes, sometimes it cannot mesh the supports completely. That's the problem. So then you can tackle that by reducing this size. The supports, you can reduce the mesh size for it, but it will take super long. Okay, so for that, let's just go with my part, I guess. Okay, let's go with my part. Still recording, right? Yes, we are. Okay, let's open up something. Where is it? And one more thing, when you do your process and you get your results like the plots over here and here, remember to click on this save simulation. It will create files. Like if you open this part now, I've opened the part that I use at the start. I'll just click on load simulation process and it will load everything for me, like the mesh file, the simulation file, the result file, and then I can like use the results anytime I want. So it
Hmm.
has opened up for me. Just I'll click on thermal. and it will give me the thermal results. So always remember to click on here. Okay, so these are the results I have: the temperature plot, the distortion plot. You just record all that, inspection results, and for the part quality, the most important parameter or result is this one, the stiffness curves. So from here you can determine at what part the stiffness is high. Like, let's say this part, it will be fixed from these holes, right? Because you can see the counter bores here. It's a part that is, it has fixed constraints over here and maybe a load here and here. So it will be facing loads in this direction, so it is bending over here, so we need higher stiffness here, like in, like it should not bend here in this direction. So for that we need stiffness in this part, and if you simulate other orientations, you will receive different curves according to how you orient the part. So in the part quality, you can use this plot to explain why this orientation is better than others and why you should go with it. All right, so you can talk about part quality here. And I guess that answers our question number 3. Yes. And then all of the rest of the parts are just logical. You just answer them based on your logic. That's it. That's all you have to do in assignment 2. All right.
Hmm.
So do you have any questions?
I don't know, like about the support, it's still giving me errors.
Okay, I'll stop recording and I'll